In this example, we'd like to find a power series solution to the second order differential equation with constant coefficients. It's homogeneous, linear. So let's remember, first of all, the formulas for the different power series representations of these things here. So our power series representation of the function y itself, this is the one that we want to find, that we want to solve for. This is our ultimate goal. This is just equal to the coefficient sequence times x to the power n. And then as we start taking derivatives, these are just formulas that you can memorize, or if you don't understand where they come from, you can build that understanding later. But this is n plus 1 times a to the n plus 1 x to the n. And then y double prime, if we want to start with the index 0, then this one becomes n plus 2 x, n plus 2 times n plus 1 times a sub n plus 2 all to the power times x to the n. Alright, so the other thing that we need to remember here is that if you plug in 0 to these power series, it's going to eliminate everything but the initial term. So let's see what happens here. So a sub 0, y of 0 is just equal to a sub 0. So this is something we did in a previous video. You can check this though. And this is just equal to 2. A sub, or y prime of 0 is equal to 1 times a sub 1. This 1 seems redundant, but it is important if you need to go up to higher order derivatives here. In this case, you don't have to, but this is just a sub 1. And so we're told here that a sub 1 is equal to negative 1. And so actually, these two pieces of initial data for the function are going to give us our first two coefficients in our sequence, our coefficient sequence that we're worried about. Now, what we have to do to find the rest of them is plug in our formulas for the power series into this differential equation. All right, so I'll write it right here. Y double prime plus 3y prime minus 18y. It's going to equal 0, but I want to plug in these formulas, right? So this becomes the sum. N goes from 0 to infinity. N plus 2 times n plus 1. A sub n plus 2, that's y double prime, x to the n. The next one is 3. Sum, n goes from 0 to infinity. N plus 1, a sub n plus 1, x to the n. And then finally, we're going to subtract 18 times the power series for y. So this is n goes from 0 to infinity, just plain a sub n, x to the power n. This whole sum equals 0. Now, in our last example with the first order equation, we had a little bit of maneuvering to do to make sure that we could write this as a single sum. But notice we don't have to worry about that for this equation because all of our summations start with the same index, and at the same time, all of our powers of x are exactly the same. So we can do some major factoring here, and we can write this equation as, so the sum, n goes from 0 to infinity, and then we can group together all of our coefficients. So this will be n plus 2 times n plus 1, a sub n plus 2, plus, remember the 3 here, these constants can go in, right, including the minus sign. They can go inside. That arrow's a little deceiving because they go with the coefficients, right? So here we now have 3 times n plus 1 times a sub n plus 1, and then minus 18a sub n, all times x to the power n equals 0. And as usual, the idea here is that the only way for this to add up to 0 for all choices of x is for the coefficients to equal 0. And so this is how we get our recurrence relation right here. We set the coefficient sequence formula here, these coefficients equal to 0, and this is going to lead us directly to a formula for a recurrence relation. So there's our term, just copying this down. So n plus 1, a sub n plus 1, minus 18 a sub n. This has to be 0. And let's just rearrange and solve it for the largest term here, the largest indexed term. So that's a sub n plus 2. And here's what we get then. A sub n plus 2 is equal to 3 over n plus 2, a sub n plus 1. That's negative, has to be subtracted over, minus 18 over n plus 2 times n plus 1, a sub n. but that's added over, so that becomes plus. So I've done two steps at once there. What do? You have to move everything over to the other side of the equal sign. That's going to change their signs to minus and plus, and then divide each term by this term here that's in front. This, by the way, is true. This works for every n greater than or equal to 0. We have our initial data, remember, up here. A sub 0 is 2 and a sub 1 is negative 1. That has to be given to us. Okay, we can't find that. That has to be given. So let's write these things down then. A sub 0 is equal to 2. A sub 1 is equal to negative 1. Let's just check and make sure I copied correctly. I did. So that's good. And then what we can do is we can shift the index here. This one can go down. All the n's can go down 2, and then this can go up 2 to start at 2. You don't have to do this. I like to do it so that the formula is a little bit more straightforward. So now you have a sub n equals negative 3 over n times a sub n minus 1, the previous one, right, plus 18 over n times n minus 1, a sub n minus 2. And this is now true for n greater than or equal to 2. All right, now, it may or may not be possible for us to find a nice closed form for this power series equation. But what we can do is at least find the first few terms. We know these two, right? So let's go down to a2 now. a2 is going to be negative 3 over 2 times a sub 1 plus 18 over, what is this going to be? 2 times 1, right? A sub 0. And we know a sub 1 and a sub 0. A sub 1 is negative 1. A sub 0 is 2, right? And we just plug these in. So this is negative 3 over 2 times negative 1 plus 18 over 2 times 2. All right, and we can now kind of simplify. 2's cancel. This becomes plus 3 halves. All right, so this now is going to say 18 plus 3 halves. That's going to be 39 halves. Okay, let's find maybe one more, and then we'll just write down the first 4 terms of this one. So a3 is going to be equal to, let's see, it's going to be negative 3 over 3, a sub 2, plus 18 over 3 times 2 times a sub 1. All right, so you always have to go back to the recurrence relation and plug in the appropriate n's where they go. So this one's just going to be minus a sub 2, so that's minus 39 over 2. That's the previous one. Plus, this is going to be 18 divided by 6 is 3, right? So this is 3 times a sub 1, which is a negative 1. And so this is negative 39 halves minus 3. And so that's going to be negative 45 halves, right? 39 minus 6. And so now we have these different, we have at least the first 4 coefficients here. Personally, I don't see a pattern yet. There might be one, but I don't see one. So what I'm going to do is just write out the first few terms of the power series and then say, okay, if you want more, you have to continue to plug into this recurrence relation, right? So the recurrence relation is key here. So here's what we have then. A sub y is equal to a sub 0, which is 2, minus a sub 1 times x, so it's plus a sub 1 times x, so minus x, plus 39 over 2 times x squared, minus 45 over 2 times x cubed, and then this will continue on indefinitely, off to infinity, right? So this is a power series, but this is at least the first 4 terms, all right, including the constant term. So the first 4 terms of our power series solution. It's obviously not the solution if you were to cut it off at this point and leave off the ellipsis here. That it would not be correct, right? It would be an approximation, but it wouldn't be correct. Now, in practice, what you usually do is cut these off, treat them as polynomials, but there are ways to measure the error then in what you've left off. So the error in the tail. When you cut off the ellipsis, the question is, what's the consequences for that, right? And in later courses you will study that. In this course, we're just really concerned with finding the recurrence relation and then solving for at least the first few terms of that recurrence relation.